class. So yeah, as I was saying, to those who asked me earlier, I'll have the exams graded definitely before our next class. I'll grade them probably between today and tomorrow. So once I have the grades ready, I'll send everyone an announcement. Also send you the solutions, and then also I'll try to give you your grades for some of the other quizzes you have done this week as well. So but yeah, at least for the exam, which is the more important part, yeah, I hope to have that done at some point tomorrow. So um I think hopefully it went well, but yeah, I'll let you know how that was. Okay, so today we'll keep talking about conditional probability, possibly also on Friday, depending on how much we cover today. But let me just remind you of these two formulas will be used all the time. So the first one is the first one is the actual definition of the conditional probability. Okay, so this is what we saw last time. So that was a definition for conditional probability. The second one is the Bayes theorem. So this is like a definition. The second one is the Bayes theorem, which is really useful. So many things, I mean, it would be impossible to solve without the help of this theorem, but it is really, really useful. So basically what it allows you to do is to switch the order in which the conditional probabilities appear. As I was saying also during office hours, I mean, for these two formulas, I actually will probably just give them to you on the exam. I don't mind, like, it's fine because they're so important that, like, if someone forgets and messes them up, then there are many things you will not be able to do. So I think I'll just give you the formulas for each of them. So what was this one? So it was the probability of B given A times probability of A divided by the probability of B. I think that's how it went. So I'll leave it. And then yeah. And then the other one is called the law of total probability. So law of total probability. Okay, that one, it is just like a very useful way to compute probability, absolute probabilities. By the word absolute, I just mean that they're not being conditioned on anything. So it's like a useful way to compute probabilities from conditional probabilities. You'll see, again, in all the examples that we'll use today, you'll see them at play, and it's very, very, very useful. So, like, I gave you a small, more simple version last time, but it's kind of easy to see that this is like how it generalizes. So I'll just write it like in the general formula. So the law of total probability tells you that the probability of a proposition or an event is kind of like the sum of the probabilities of A condition on BI times the probability of BI. let's say from I equals 1 to n. And so what is b1, b2, b3 up to bn? There are events or propositions that satisfy the following. So the first thing that they satisfy is that they're mutually exclusive. Okay, remember mutually exclusive meant that they cannot be both true at the same time, or they can, or if you prefer that they cannot occur at the same time. So mutually exclusive is like on a given coin getting heads and tails, right? Those are mutually exclusive events, for example. And the other thing is that the union of them, or B1 or B2 or B3, etc., up to Bn, so B1 or B2 or blah blah blah, blah or Bn has probability 1, or has probability 1 of occurring. So, for example, when you throw a die, that B1 could be getting a 1, B2 could be getting a 2, B3 getting a 3, B4 getting a 4, B5 getting a 5, and B6 could represent getting a 6. And all of them they're mutually exclusive, right? None of the two can happen at the same time, but at least one of them must happen all the time, because like you're exhausting all the possibilities when you throw a dice of what could happen. So the law of total probability is kind of like a way to break the probability of a statement in terms of like kind of conditional probabilities of events that exhaust the entire space. So if you want to do like a diagram, it's like if you have like this is called like a partition. So you have like the space of all the things that could happen, and basically what's happening here is like you have B1, and then you have like B2, and then you have B3, maybe here, and maybe here is dot 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 Bn. So you see they don't overlap, but everything kind of they cover up the entire map of what can occur. And then you have like your event A, which is maybe like in here. And so what it is saying is that you can break the probability of the event A in terms like in terms of sub pieces, like you see, like by decomposing it into each piece into how much it belongs to each piece. Is that kind of making sense? I mean, it's if you think about it in terms of a diagram, it's very intuitive. And I'll do it in a sec. I will give you like an example like right away once we talk about the Monty Hall problem. So, which is what I was going to do next. Is that okay? Any questions so far, so good? So again, like I guess I'll probably give you this, like, I'll give you these 3 formulas on the exam for the next exam, like, because they're kind of useful to have, and I don't mind. That's fine. So let's talk about, the Monty Hall problem is a good example to put all of this together. So let's start there. Did everyone see? Did you watch, all of you, the Monty Hall problem? I was probably going to do like a refresher on what it was about, but I'm curious if everyone saw the video that I had sent.
Yeah, I did.
It's a cute video. Yeah, it's like a nice one. So, and it's a classic problem in probability because it's so confusing and like it really takes a little bit of time to. I mean, it's kind of one of those things that you maybe are persuaded that like what it's supposed to be, but you're not intuitively confident that that's the right answer. You know what I mean? So in the Monty Hall problem, you know, you have 3 doors, right? So you have 3 doors, and only one of them has a price, right? Only one has a price. Right? The price, like it depending on the variation of the Monty Hall problem, could be either like a car or $1 million, whatever you prefer. And then again, depending on the version of the problem, the other 2 doors just have goats or are empty. Okay, but the point is that 3 doors, only one has a price, and so you will choose your. So the setup of the problem, which I think was like in a TV show or based on a TV show, back from the 70s, 60s, like some decades ago, is that you choose like one of the doors, right? So here's like step 1. Choose one of the doors. And then what happens is after your choice, that's important, you have the host. The host does know where the door, the price is supposed to be. So in step 2 is that after your choice, like the host will open one of the 2 other doors, right? Host opens one of the other choice, one of the doors you didn't choose. And I think a list of one of these 2 doors, you know, for sure, like at least like it could be that both have nothing, right? Like let's just to make it more concrete. Like I could have said I'm going to choose door 1, right? If I say I'm going to choose door 1, it could be that the price was already in door 1, right? The host, he will not open the door. What he's just going to do is like from between door 2 or door 3, he's going to show one of those 2 that had no price. So the host will always show you one of the doors without a price. Okay, so if you had already chosen the correct one, the host had to, you know, had 2 choices to make. And if you had started choosing the incorrect door, there only one had of the 2 remaining, one had a price and the other didn't. So like the host would be forced to choose the one that didn't have the price. What I'm just saying is that what I'm trying to say is that the host will always be able to open a door with no price. So after your choice, host opens one of the doors you didn't choose, and that also doesn't have a price. Okay, and so the question of the problem, right? And so at this point, like this is where the climax of the Monty Hall problem occurs, because that now the host opened one of the doors. Let's say the host opened door 3. So I'm choosing door 1. The host opened door 3. So door 3 had nothing. So the host will ask me, do you want to switch, right? Do you want to switch to door 2, right? Because again, I still haven't seen what's behind the other doors. So we don't, so, you know, there's like, so the question or the problem is, should you switch? Should you switch to the remaining door you had no, to the remaining door, to the other door? So like, again, just to do it for our, this is the one that I'm going to analyze. So in our example, like say I chose door 1, in step 2, the host opens door 3. And so my question is, should I choose door 2? Right, so is it reasonable to choose door 2? I see like a good strategy. Okay. And I'm like, I don't remember how long ago I heard about this problem, but I'm pretty sure that my first answer was like, well, it shouldn't make a difference, right? And I think that's kind of what everyone would think if you just hear it out, because you're like, well, I mean, now there are only 2 doors left, right? I mean, it should be 50-50 chances of one having the price, right? So like, it shouldn't make a difference which one you choose, you know what I mean? So that's kind of, I think that's kind of like the visceral reaction, like one would have to, okay, then, let's see. I think the fact that I think switching before he opens, I would have to think about it, but I think switching before he opens, that shouldn't matter. Like the key fact is that you are making a choice after he opens the door. So because that's what's introducing the element of information that you didn't have into the problem before. So you know, the thing that what makes this interesting is that the host does have perfect information about where the price is. So kind of like the effect of like the fact that he's always choosing one of the doors without a price, it is kind of having like we'll see what once we do the computation, it will have an impact on what the strategy is. But it's only after he introduced his information into the problem that kind of that tips the scales for the setup. Before he has made a choice, before he has opened any doors, I guess yeah, it doesn't matter like what you're doing, if that makes sense. So okay, so I guess I have to read what you were saying. So what if we switch before he opens the door? Okay, but you're saying, okay, so you're saying like I chose door 1, and then before he opens any door, I choose door 2. Is that what kind of you're saying? Like, I guess I would need you. I mean, probably if you want to mute yourself, like I would probably try to understand. I'm kind of yes, like I'm not like I'm trying to see what if I understand the setup. Yeah, you want to talk? Feel free to.
Yeah, I was just saying, like, let's say we pick door 1, and then
Mhm.
we kind of, before he opens it, we just quickly change it to door 2. I mean, door 3, right? And then,
Right.
but he still opens the same door, but but according to the strategy, we would have to switch back.
Okay, so you're saying like, for example, I have chosen door 1, right? And I'm going to choose door 3, right? But the thing
Yeah.
is, like, he may not choose, like, now he may not open door 3 necessarily, because it could be that door 3 had the price, right? So it's not that, I mean, once you decided to choose like a different, if you choose to switch doors before he opens anything, that kind of is changing his strategy, right? Because his strategy does need to depend on what you're doing, if that makes sense. I mean, let's talk. These problems, these variations can be confusing, but I think what I'm trying to say is that you choosing you switching right before he opens the door, it's kind of like restarting the problem with a new door. You know what I mean? Because like until then, he has played no role. So I would go with that makes no difference, but I would have to think about what you're saying carefully. But my gut feeling is that yeah, it's only after he has done a move that the problem, like there's like asymmetry being introduced in the problem, not until then. But yeah, we can discuss it. I mean, Yeah, we can discuss it if you want during office hours. But it can be confusing. But yeah, I would say you have to be careful how you set it up. But I don't think it would make a difference in that case. It's just that it would change what he's doing. That's what I've been trying to say, right? So, but yeah, that's how I would say it. There's on Wikipedia, there's actually a lot of variations of this problem. It may be that one of the ones you're talking about is there, but yeah, if I understand it correctly, I don't think it makes a difference. But yeah, you can. I definitely wouldn't like try to make a statement until I have thought about it carefully, because this problem can be a bit confusing. But yeah, let's just so, because this is the one that I had calculated. Let's stick with like I chose door 1. He opens door 3. So now we know for a fact that door 3 has nothing. So the question should be, do you switch to door 2? Okay. So what I'm trying to compute, right, it is like what I'm after. I'm trying to write it in a way that uses this conditional probability stuff. What I want to know is that the probability that door 2 has the price, right? Given that the host opened door 3, right? So that's what we're after. That's a conditional probability that we want to know. Because like, again, the conditional probability involves like an element of information you have gained. So now we have gained the information that the host opened door 3. Now, obviously, this is the entire goal of the problem. So it shouldn't be easy to compute. But what you can do is use a Bayes theorem. And again, the magic of the Bayes theorem is that it allows you to switch the factors in the conditional probability. And again, that happens to be a lot, very, very, very useful. So by the Bayes theorem, this is the probability of host opens doors 3. Like I can put it in present tense. Given that door 2 has price, oops, like I will need, I mean, this is, let me write it more succinctly. Host opens 3, given that 2 has price, times, right? What's that? The probability that 2 has price, divided by the probability that host opens door 3. Is that making sense? Like how I'm applying the Bayes theorem? So again, like in the Bayes theorem, the way I'm writing it, this is kind of like A, and in the formula from before, this is A and B, right? So again, it's like the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. Is that making sense? Okay, so so what's the okay, let's start with each factor. What's the probability that host opens? Let's start with the first one. So, oops. Yeah, let me. So what's the probability that a host opens 3 given that the door two has the price? What is its probability? What would you say?
Is it 1?
It has to be 1 because by the rules of the game, the host can never
He has
open
no
the
choice,
one.
right?
Right. The host can never open the door that I chose. The way I explained the problem, I chose door 1. So that only left 2 options to the host, but the host has to always go for the one without a price. And if the second door has the price, then that forces the host to go to door 3. So yeah, the host has no freedom for this probability. So that's why this one has to be 1, right? Because host can't choose my same door, my door, and 2 has the price. Is that making sense? So this one is fun. Then comes the other one, which is the probability that door 2 has a price.
Is it 1
What
over 3?
It is 1/3 because yeah, at this point, like this has no other information. So if you have no other information, like you're assuming that the prices were like arranged were assigned randomly. So like on average, or like 1/3 of the times, it will go to door 2. So that's why this one has 1/3 of possibilities. Okay, and now comes the one that's a little bit confusing, which is the probability that host opens door 3. What do you think that one is?
Is
Yeah,
it
you
1
wasn't-
over?
1 over what?
Is it 1 over 2? Because it can't.
Well, tell me.
Because it can't open the door with the price, right?
Yeah, it does have to be 1/2, but here it is less. I do think it's less clear why it is 1/2, right?
There's only 2 doors he could choose from, right? Because we chose 1 already, right?
Yeah, I mean, right, but it is, okay, yes, but that is kind of how you should, but it can be less clear.
No,
because
isn't
then
it
you-
because he can't choose the door of the price? Because the rule says he only choose the door that is not the price, right?
Right,
So he
right.
only has 2 options.
Yeah, but and then you have to think here, like, are the options equally likely or things like that? Okay, so okay, so if you're convinced that it was 1/2, that's good because that's going to be the answer. But you know, if you want to be more careful, like there's a way to actually justify doing a calculation. To justify doing a calculation, you have to do the law of total probability. So this is why I mentioned it at the beginning. That what the law of total probability says. Let me write it here. And this will clarify the things. It is that this probability is the same as the probability that the host opens 3, given that the price is in door 1, times the probability that the door 1 has a price, plus the probability that the host opens 3, given that door 2 has a price, given that the times the probability that door 2 has a price, plus the probability that host opens 3, given that door 3 has a price, times the probability that door 3 has a price. Why? Because the idea is like the price is either in door 1, in door 2, or in door 3. Those are 3 mutually exclusive events, and those are the only three things that can occur. So what I'm saying is that the probability kind of breaks up into pieces corresponding to each of these possibilities. So it is there's like a fraction of the probability that's coming from the case where the price is in door 1, another fraction coming from the case where the price is in door 2, and another part of the probability is coming from the case in which the door 3 has the price. You see what I mean? So that's why this the thing is, like, each of these conditional probabilities is way easier to compute. So that's you know, if you are ever confused by how to compute certain probabilities, you can use the law of total probability to kind of break them down into pieces that are more easy to understand. Is that making sense? We're about to compute each of them, but you'll see it's a lot easier than trying to convince yourself verbally, which is kind of what otherwise you would be stuck doing. So that's fine if you kind of feel that you know the answer, but otherwise it's better to try to have something else that backs it up. So you can do this. So each of these probabilities of the door having the price is just a third, right? Because again, each door has a third of the chance of getting the price. Now here comes the nicer ones, like the easier ones to compute. So if door 3 has the price, what's the probability that the host opens the door 3? That one is easy.
Zero.
It's 0 because the host can never open the door with the price, right? So this one is 0. Is that making sense? And
Yeah.
and then so yeah, this one is host can't open price door with price. Then this one that there's one that we already computed. The host opens door 3 given that 2 has a price. We already had found that this one was where did I write it? That one was 1, right?
1.
Yes. Good. So perfect. This is what we did before. And then if door 1 has the price, right? Then you're thinking of what's the probability of the host opening door 3. So now you have the host does have between doors 2 and 3 to open it, right? So that one should be what, 1/2, right? Because now there's 2 choices for the host to make. So you get 1/2 times 1/3 plus 1 times right, 1 times 1/3 well plus 0 times 1/3, which actually won't count, right? But that's fine. I'll write it anyways. So it's right, it's 1/6 plus 1/3. Did that? That's correct. So it was 1/2. Is that okay? Is that making sense? So you see, like, that's a cool way to compute the probability, because kind of like it kind of is a way to compute the probability by analyzing every possibility. Every possibility was like the door being in a particular, the price being in a particular door. So the law of total probability is kind of like a breakdown of the probabilities in a way that's very useful in practice. So if you plug all of this back in, let's just go back. So this is what we were computing. Oops. So let's go back to the formula that we had. So what does this become? So we just saw that this probability was 1/2. We saw that this one was 1/3, right? And we had said that this one had to be 1, right? So overall, you get 1/3 over 1/2. So you get 2/3. But the Bayes theorem that had to be equal. This is also the probability that 2 has the price given that host opens the door 3. So yeah, now the chances. So that means that the chances for. Now that means that the chances for door 2 having the price are bigger, right? Like they're 2/3. So it does make sense to switch. So the solution of the multi-hole problem is to switch. Is that okay? Okay. So that's a good example. That's a nice example of conditional probability. It does bring a lot of different elements into play. So it's a good example to keep in mind for how conditional probability is supposed to work. Now, let's do another one that can be confusing. This is another one that's can be paradoxical, and in fact, it's kind of one of these questions that has been given to students like in classes, and students like kind of get over on heated arguments about what the answer is. So this is another fun example. So let's say you have like a box or like an urn, but let's call it like a box. So you have a box. So you have a box with 2 black balls and let's use 2 green balls. Okay, so there's only 4 balls inside that box, and we're going to. So here's the setup of the problem. I'll give you a chance to think about it first before we discuss it together. So you're going to take a ball, right? Like imagine, like again, kind of you close your eyes, whatever. Everything has been shuffled pretty well. So you're going to take a ball, and once you take a ball from the box, you don't put it back in. So after you take the first ball, there's only 3 balls left, right? So here's like the first question, which is like not too bad. So here's the question 1. And again, if you know the answer, don't say it so that people just can have some. I'll give everyone like 5 minutes to think about this. So what's the probability of picking a green ball on the second time if the first time you picked up a green ball? So again, don't say the answer because I'll give so again, like in this problem, you pick up a ball and don't put it back in, right? So in this problem, when you pick a ball, you don't return it to the box. So again, like on the first one you grab is a green ball. So what are the chances that the second one you grab is a green ball as well? Now comes the fun. The fun. So that one is not too bad, but I'll again give you a chance to think about it. The second one is more interesting. It is, what are the chances that the first time you pick a green ball, if on the second time you got a green ball, you picked up a green ball? So to make this more concrete, like you could imagine, like you pick the first ball blindfolded, so you don't know what the result is. And then when you pick the second ball, you find that the second ball was a green ball. So now I'm asking for what's the probability that the first one that I picked was green as well. Okay, but notice that they are slightly different questions, right? So think let me give you everyone 5 minutes to think about it, and then we'll talk about the answer. But this is like a fun problem to discuss. So let's meet in 5 minutes and we'll discuss the solutions. Okay, let's see. How's everyone? What's the answer for the first one? Did anyone think about it?
It's 1/3.
Yes, that's correct. Did anyone find the second one?
Calculating, almost done.
Okay. Yeah, I think I still haven't had like 5 minutes, so let me give everyone like 1 or 2 more minutes. Think about it. If someone finds it, you can put it on the chat. Okay, so anyone want to give it a shot? What would be? The second one is a lot more confusing. I hope you find it more confusing. So what usually is like a source of like concern is that people would say, how can what you got on the second time affect what you got on the first time, right? So they get into this mindset of like, what's the connection? What's the causality or the causal link between you getting something on the second time and you having obtained something on the first time? So they think of this as kind of somehow influencing the past or something like that. But that's kind of like the point of all this. What I'm trying to emphasize with these conditional probabilities, like a statement about conditional probability is not about whether something causes another thing or things of that sort. It's more like how your information should be updated or changed based on new evidence, right? So it's kind of more like about information that you have on a situation versus like you having had like drawn like a particular ball on the second time, influencing like what happened on the first time. That's not what it means. So if once you try to get rid of that idea, like it's less paradoxical that you can ask these questions. So like the first one is really straightforward because in the first one, like let me write it this way. Hopefully this makes sense. So what do I mean by Smith notation? I mean the probability of getting green the second time, given that I got green the first time, right? So it is true that's 1/3. Why is that 1/3? Because in the problem, I'm not putting the balls back. So if I grab a green ball on the first time, that only leaves one green ball. There's only one green ball remaining and 2 black ones, right? So after grabbing a green one, a green ball, there are 2 black balls left. And one green one. And that's why, assuming everything is being mixed properly, like you would, shuffled, you would say, oh, it's 1/3 chance. Okay. Is that making sense? Is that plausible? Everyone kind of believes that.
I think I got the same answer again, but I think
Yeah,
I've
good,
got
good.
something wrong.
No, that's good. That's good. No, you did it well. But
Oh,
it's for
it's
different.
1/3.
Yeah, but for different reasons. That's what I'm trying to say, right?
Oh,
It's kind of
okay.
like it's fine if the numbers are the same, but it's kind of like important to notice that there are different questions, right? So, but yeah, it's good. It's supposed to be
Yeah,
one.
because
It's
I couldn't answer. I mean, I got 1/3 and I was really confused because it was the same answer.
right.
And
No,
I keep calculating again and again. I thought I typed something
no.
wrong.
Good. No, it is. That's the thing, right? Like, it's kind of it's more of a coincidence, I guess, that it was the same. But like the important thing is kind of like to realize that first, like you can ask this question, right? That the question makes sense, and that doesn't. Again, it's not when we are computing these probabilities. It's not that we're asking for something mystical about like your choice. Like if you thought about this happening in the future or in the present, it's not about your choice in the future affecting your choice in the past or something like that. It's just like more like about information that you have about different events. So again, like when the probabilities are hard, when the conditional probabilities are hard, the philosophy is to use the Bayes theorem. That's kind of what needs to get stuck. That's the most important like lesson of all of conditional probability. Use the Bayes theorem whenever you can, because it allows you to switch the probability orders. So if you use Bayes, you can write it again as probability of green given green 1 times the probability of getting a green 1 on the first shot divided by the probability of getting a green 1 on the second shot. Okay. So what I'm trying to say is that this is way easier to compute each term individually. Okay. In fact, the first one we already computed, right? Like that's actually what we did in part 1. Okay. So this we just found is probably if this is 1/3, right? This is from the previous part, right? And then there's another one that's easy to find, which is like this one. What's the probability of getting a green 1 on the first attempt? What's that probability?
$2/4.
Right, 2/4 because there were 2 green balls, 2 black balls. So 2/4 or 1/2. Good. Okay. And then comes the one that's slightly more fun, which is what's the probability of getting the green one on the second attempt? And at this point, you have to be like, well, it actually kind of depends on what you did, you know, it does depend on what happened on the first attempt, right? And that's where you have to use the law of total probability again. So you know that on the first attempt, you either could get like a green or a black. So what we're going to, and that's the only two things that could happen. So we're going to break this probability into a sum of two probabilities. So if you use the law of total probability, this is the probability of getting green in the second time, given that you got green the first time, times the probability of getting green the first time, plus the probability of getting green the second time, given that you got black the first time, right? Because like the two colors are green or black, times the probability of getting black the first time. Okay, that's how that breaks down. Is that making sense? So again, that's where the law of total probability becomes really useful, because kind of to compute this probability, you do have to consider the cases. So the law of total probability allows you to consider like the cases in a very systematic way. Okay, is that making sense? So these we had already found. That's good. We had already found that this to be 1/3, right? That's what we did in part 1. The probability of getting green, we also found before, this is 1/2. Okay, the probability of getting black on the first time, it is 1/2, because exactly of the same reasons as in here, right? So this is 1/2. And now this is a last one, which is kind of fun. What are the chances of getting green the second time if you got black the first time? So what are those chances?
2/3.
2/3, because exactly now you know there are 3 balls left, 2 are green and only 1 is black, so it's 2/3. Is that making sense? So, and now you just put everything together, so you get well, it's 1/3 times 1/2 plus 2/3 times 1/2, and what does that give you? It gives you what? 1/6 plus 2/6. So this is 1/2. Oops, this is 1/2. Yeah. And so that's what goes into the denominator. So we're ready to go. So if you plug that all of this into the base theorem, now we know that this probability of getting green was 1/2, and this one of getting green the second time was 1/2, and the probability of getting green the first time was 1/2 as well. So the 1/2 cancel, and then you end up just with 1/3. Is that okay? But again, kind of like the good, like what I like about this example is that it gives you like a sense of the actual asymmetry between computing the conditional probabilities in one order versus the other, right? This is a lot more difficult than the one we did at the first step. So that's kind of like what shows you the power of the Bayes theorem, because it just gives you like a systematic way to compute like the difficult conditional probabilities. That making sense? So, okay. Okay, now let's move to a very important topic, It's still related to conditional probability, which is independence. This is one of the most important topics in all of probability. So first, I'll define something for you, which is kind of useful to have. So here we're going to have two events or propositions. Each with positive probability. So I just mean that the probability of A is positive and the probability of B is positive. Okay, both are, sorry, greater than 0. They cannot be greater than 1, right? Because they're probabilities. So there's something that you can define as a correlation between the two propositions. So the correlation of the propositions yeah, I'll use the same notation. Well, would that be confusing? Well, let's call it core. Yeah. Okay. So let's define that. Now, the first thing is that actually there's a this I mean, it's kind of, I mean, of course, after you thought about it for a while, it is like a natural definition, but let's try to think about what it means. So let's think about it. Yeah. Okay. So what other ways are there to write this formula? What does this remind you of? What is that formula equal to?
Bayes theorem.
Well, it's actually, I mean, just this piece is a little bit before Bayes' theorem.
Isn't it the probability of A given B?
Yes, that's correct, but that's just the definition. Like the Bayes' theorem is when you want to relate both of them, but yeah.
Oh, yeah, that's right.
So yes, just this part is the probability of A given B, but I still have left over the probability of A, right? And also this, you know, would be the probability of B given A divided by the probability of B. Okay, so the correlation can be written in 3 ways. Kind of this, if you write it this way, it's a lot more symmetric, right? If you write it this way, it's more symmetric. It looks more symmetric between A and B. But if you write it in this way, you see it's kind of more suggestive of certain things that I'm about to say. So that's a formula for the correlation. Okay. So okay, so that's just like a definition, right? Now comes like the first important formula, or like a second definition, which is like the two events are positive correlated if the correlation coefficient is strictly greater than 1. Okay, so let's think about that, what that means. So here's a definition. A and B are positively correlated if the correlation coefficient is greater than 1. Okay. So what does that mean? So what does that mean? Like conceptually, right? Why is this? Why are we giving this name? Well, if you look, for example, at the second version of the formula, right? It would say, this is saying that it doesn't matter which one you take, but this is saying, for example, that the probability of A given B divided by the probability of A would be greater than 1, right? Because these two are equivalent. This is equivalent to the correlation coefficient. So what does that mean? This is saying that the probability of A given B is bigger than the probability of A, right? So in the positively correlated case. So what this is saying is that if you know that B occurred, right? So what does this mean? This means, what does this mean? Like, it means like, you know that B happened. So now what are the chances for A to occur or of A being true? So what this is saying is that if you know that B happened or B is true, then the chances for A have increased, right? Because this probability is bigger than the original one. So this means that if B is true or has occurred, so if B is true or has occurred, now the chances of A are bigger, right, than before. Is that making sense? Since the conditional probability is larger. And again, like, this is how people use the word, like the phrase in normal life, right? So like, you could actually make this very concrete. Like, you could say, well, A is getting a good grade on the exam. And B could be like studying hard, something very dumb like that, right? So you're saying that the chances of getting a good grade on the exam, given that you study hard, are bigger than the chances of just like, you know, like getting a good grade if you don't know anything else. Is that making sense? I mean, that's what you would expect, you know, that there's like a positive correlation between studying and like getting a good grade. Otherwise, there would be no point in studying. You know what I mean? So that's kind of like here, like you know, common sense, like of what you mean by studying, like should tell you that these two events are positively correlated. Is that making sense? So these are like positively. And this is like what all of nutrition science and all of medicine is all about, like, you know, finding correlations between, well, if you eat this, then you have this heart disease rate, or you have like these chances of getting this, et cetera, right? So positive correlation is like all over the place because of that. And then what, okay, is this definition making, hopefully this definition now makes more sense with this example. Is that okay? So now, what do you think is the next definition that you could make for two events or propositions to be negatively correlated, right? So here's the second part of the definition. AB are negatively correlated. What should happen in this case? What should I put here?
Less than?
Yeah, it's just less than 1, it's strictly less than 1. Because in this case, oh, sorry, I'm calling it G because that's one notation that the book uses. I mean, not this book, not a different book. yeah, if the correlation between the events is less than 1. Because again, what this is saying, like, right, secretly, this is saying so this so this means if it is more convenient to write it in terms of this version of conditional probability, it means that now the probability of A given B is less than A, the probability of just A. So kind of like B being true has lowered the chances for A to occur, right? So it's kind of playing against A. So B being true or having occurred has decreased the chances of A being true or occurring.
But what if like A and B are not very correlated? So can the probability of A given B still equal the probability of A?
Oh, that actually, you're asking about the extreme case, right? Where I have equality, right? That's actually called independent, and that's like the last part of the or uncorrelated. Yeah. But here it is. Like, it's really important, right? I'm not saying by what amount the chances have increased, right? So the chances could change from like 10% to 10.0000001%. But those are increased in chances. You know what I mean? So here I'm not. I'm just saying that the chances increase or decrease. I'm not quantifying by what amount they increase or decrease. But yeah. But yeah, the last case will be the independent case where you have a strict equality. But it's kind of, I prefer to start with these other two because it may be a little bit more natural. So yeah, like like in the negative correlation case, what this is saying is that if B occurred, then A has a smaller chance of occurring. So again, like you could not to like try to make medical advice or anything, but you could have like B represent smoking for all your life or smoking 10 packs of cigarettes every day or whatever. Like you put B whatever you want to make it smoking every day a lot. I mean, just like whatever you want. Here, of course, you could quantify it if you wanted, and then A could be, I don't know, living more than 80 years. So give me whatever number you want. And presumably you would expect that your chances decrease, right? Like that's what you would, like that's what's supposed to say that smoking is bad for you, among other things, right? So A could be like living more than 70 years or whatever. So I mean, put whatever date, age you want. But like the idea is like, right, it's here, like smoking is supposed to go against you, right? So that should decrease your chances of like living more than 70 years. Okay, so it's like a very small, like silly example, but it's just to give you a sense that that's actually how people use these words in practice, like in the real world, right? They talk about correlations and things of that. And then we come to the third part of the definition, which is I gave you the case greater than 1, less than 1, and of course, like the leftover situation is like exactly equal to 1, right? So the last case is kind of the most important for us because that's where you can do a lot of probability calculations. The last case is when A and B are independent. If this correlation coefficient is exactly 1. Okay, so again, what that means, like, it's kind of actually there's two ways in which it's useful to write it. So the first way to write this is to say that then the probability of A given B So this means two things. That the probability of A given B is the same as the probability of A. So now this means, what this is saying is that knowing B doesn't help you at all in knowing anything useful about A, right? Because B is not giving you new information for or against A. So B is not giving any information in favor or against A. Is that making sense? So that's so independence is kind of like saying like the knowledge that you have among them, they don't knowing something about B doesn't give you some useful information about A. And then another way that's very useful to write the independence condition, which is typically how you would write it, that's like the more common one, is that if you look at the original definition of the correlation coefficient, it was this ratio. So if you set it equal to 1, that means that the probability of the intersection is the product of the probabilities. So the more useful way to write this for calculations, this means that the probability of A intersection B is the same as the probability of A times the probability of B. Is that making sense? So this is like, again, for A and B independent. And that's usually how you'll see like the definition of independence, like many times, just like straight out that written this way. But so that's kind of and it is secretly we have used this a lot of the times when we were computing probabilities before. So many calculations implicitly, almost 90% I think of the problems we solved kind of had like a hidden independence assumption. So many problems we have solved so far use that condition implicitly, secretly, without saying it out loud. So many problems we have solved. Okay. Like for example, like here's like an example where we use this all the time. You have two coins. Right? A could represent getting heads on the first coin. And B could be getting heads on the second coin. And I mean, like, if I had asked you for like the probability of getting heads on the first coin and getting heads on the second coin, you would just say like that's 1/4, but you can think about it as 1/2 times 1/2, right? So this is like the probability of A times the probability of B. You see, so almost again, there are like tons of problems that we have used where the assumption of independence have been made implicitly when we were counting things, because we kind of were saying like when we were counting things, sometimes we were implicitly assuming that certain events didn't affect the other, like how likely the other events became. Is that making sense? Now, here's like a question that always gets discussed because it can be very confusing. So here's like a conceptual question, which is good to have on your toolkit. So conceptual question. Can two events which are mutually exclusive be independent? What do you think? Can that happen or that cannot happen? Yeah, they cannot be independent, right? Because what does it mean? What does it mean for A and B to be mutually exclusive? What does it mean for A and B to be mutually exclusive? It means that their intersection, like the probability of they occurring at the same time is 0, right? Because like the intersection or like the and is a contradiction, right? So like the probability of A intersection B equals 0, but there's no way that's going to be, I mean, unless one of them has probability 0, in which case we don't care about it to begin with. But this is not going to be the probability of A times the probability of B. But it kind of makes sense because, like, again, mutually exclusive are kind of opposites of events, or propositions are kind of things that can never appear at the same time, right? So if you know that one happened, that gives you a lot of information about the other one, because you know that the other one cannot take place simultaneously, in a sense. So like, in a sense, mutually exclusive is, in fact, what's the correlation coefficient for mutually exclusive? What is the correlation coefficient? It is 0, right, in the mutually exclusive event, right? So they're negatively correlated. They are as negatively correlated as they could be. Is that making sense? Because the correlation coefficient is always non-zero. I mean, non-negative, because it's a a ratio of positive, non-negative numbers, or positive numbers. So in fact, mutually exclusive events are like negatively correlated. And that makes a lot of sense, because if one event happened, that kind of kills the chances for the other one to occur, right? Because they're exclusive. Is that making sense? Just give me a second. Is what I'm saying making sense? Yes or no? Is that okay?
Yeah, no problem.
Okay, good. Now here's another fun thing to check. This is another useful property to have. Here's another fact. It's easy to check, so we'll check like a couple of them. So here's another useful property. if A and B are independent, then A and B complement, A complement B, and A complement B complement are all independent. Okay, let's try to work that out. Let's just do one of those. Let's do the first one because the others are kind of similar. Let's see if I get it right. So kind of once you know the independence between two events or two propositions, you kind of know the independence between the among the propositions and their complements, or the complements of those propositions. So let's try to do let's check. So we know by hypothesis, like the hypothesis is that the probability of A intersection B is the probability of A times the probability of B. And I want to check that. So I want to check, let's check this for A and B complement. So let's check whether it holds for B and A. Okay. So what I have to check here would be whether the probability of A intersection B complement, I don't know whether that would be the probability of A times the probability of B complement. Right? But is that making sense? So that's what I want to check. So let me just start. Which of the two? I don't know which one you prefer, but for me it's easier to start with the right hand side. Okay, so let's start with this side. So what is that equal to? Anyone can tell me? What property could you use here? How can I use it, re-express this in a useful way? What's the probability of B complement? I guess that's my question.
One minus probability of B.
Yes, good. This is 1 minus probability of B. And so this is probability of A minus probability of A times probability of B, right? And then what is the probability of A times the probability of B? That's the probability of, by the independence, that's the probability of A intersection B, right? And now the question is whether this is clear that that should be the probability of A intersection B complement. Here, I mean, you kind of have to do like a Venn diagram to convince yourself that that makes sense, because maybe you have A here and you have B complement. Here you have B. So in fact, let's make B like half of the box. So here you have B is all of this, just for diagrammatic purposes. So when you look at A intersect B complement, you're looking at like the stuff outside of, let's say B is like this green thing. So you're looking at the stuff that's not in B. So it could be this stuff, but it also has to be inside of A. So this is actually the stuff that we're after. This is what the probability of A intersect B complement would be like in this picture. And yeah, it kind of makes sense that it would be the size of A in a sense, which is the probability of A minus the stuff that A and B share, which is what's in here. So what I'm trying to say is that it does, I mean, it is correct that this is this thing does happen to coincide with the probability of a intersection. Okay, and the others kind of follow by the same logic, just by making a couple of quick calculations and some Venn diagrams in that way. Is that making sense? I mean, it's kind of more a useful thing to have in practice. So. Okay, let's see. Okay. Okay, now here's another thing that is kind of here's another question. So today I'm trying to kind of clear up some of the more theoretical things, because like the problems, they do take a little bit more time to do, and so I want to do those on Friday. Some examples involving independence. They're kind of fun. So let's see. Let's do. I'll skip this one. Okay, here's another conceptual question that is kind of fun to think about. If the correlation of A and B is greater than 1, and the correlation of B and C is greater than 1, so this means that A and B and C are positive correlated, right? So does it follow that the correlation between A and C is positive, is greater than 1? What do you think? So that A and C are positive correlated. So for those of you who have seen this in other terminological jargon, like what I'm asking is if being positively correlated is a transitive property. So for example, what is a transitive property? What's a transitive property that you may know of? Let's see. Okay, what would be a good one? Okay, so it is kind of like if A is taller than B and B is taller than C, then you would like to say that A is taller than C. For example, that's like a transitive property. One that is in human life, one that is not transitive is like, for example, if A is friends with B and B is friends with C, it doesn't follow that A and C are friends, right? So that's not a transitive property. So I'm asking whether correlations behave like height, more like height, or more like friendship, right? Whether it it is transitive. So if you had to make a guess, and I think that's the last thing I'll do for today, but if you had to make a guess, what would you go with?
No.
Yeah, well, right. Is it clear that it's no? Like, I guess that's the other question. So let's see, where did I have this example? Because this is a nice one. Here it is. Yeah, it is not it actually it's not necessarily true. So yeah, it's not transitive. So it's one of those things you have to be careful about. So no in general. So for example, just to, and yeah, I'll finish with this because like I already feel like gave you a lot of information today. So imagine that you're throwing a die. A third, or I will use it in plural just because it sounds too weird to me in singular. A third dice. I know. So A could be represents getting 1 or 2 or 3 or 4. So that's what I mean by this notation. It just means that A represents getting a 1 or a 2 or a 3 or a 4 when you throw the dice one time. B could be getting like a 2 or a 3 or a 4 or a 5. And C would represent getting like a 3 or a 4 or a 5 or a 6. And so A intersection B. So what's the correlation between, sorry, the correlation of A with B? Well, it's the probability of A intersection B divided by the probability of A times the probability of B, right? But what does it mean? What is A intersection B? Well, it's like the probability of getting, like, what are the two events? What are the things that these two have in common? It would be either getting a 2, 3, or 4, right? So it's like the probability of getting 2, 3, 4 divided by the probability of A. The probability of A is 4, 6, right? Divided by the probability of B. The probability of B is also 4, 6 because there are 4. I'm including here 4 possibilities. So it's 4, 6. And so I get so, and this probability, since there are 3 sides of the dice that I'm referring to, is 1/2. So it's 1/2, and this is divided by 4/9. If you simplify this a little bit, so you get 9/8. Okay. So that means that A and B are positively correlated. Okay. So what that means is like, again, like if you knew that B happened, then you have higher chances now of thinking that A occurred, for example. That's what it means, positive correlation. And you can also check if you want, I'll leave that to you, it's like the same calculation. You can also check that the correlation between B and C is 9/8. Okay, it's kind of like very symmetric, this example. But what is the correlation between A and C? So it's the probability of A intersection C, the probability of A times the probability of C. Okay, but what does it mean A intersects C or A and C? What's the only way for these two to happen? Like it means that you have to get like a 3 or a 4. That's the only way for both to happen at the same time. So it's the probability of getting a 3 or a 4. And then again, the probability of A is 2/3. And the probability of B of C is 2/3. But now, since there are only 2 sides in this coin, since you're only referring to 2 sides of the coin, that's 2, 6. So it's 2, 6 divided by 4/9. And that gives you 9/12. which is less than 1. So here again, you have to be careful being positive correlated. Like if A is positive, so what this is saying is that if A is positive correlated with B and B is positively correlated with C, it doesn't mean that A and C are positive correlated. Same for negative correlation or independence. So you have to be careful with those things. Okay, so like the conditions don't you cannot just like assume. Sometimes you want to assume properties that are not really there, so you just have to be careful when doing those things. So unless something has been explicitly stated that it works, you shouldn't assume that it works, because then you can just fall prey to very silly mistakes. Is that making sense? So it's kind of more like a thing to be careful, to not be careless with these things. So what we'll do on Friday actually is do some examples, some more examples with this independence idea. And basically you can talk about conditional independence. So we'll talk about that, and once we get to that, we can do some fun things. Which is like there's another famous paradox called the medical test paradox, which is pretty fun to work out. But for that, we need to talk about conditional independence. Okay, so again, I think this is a good place to stop. So I'll send you in a couple of minutes like the information for the quiz on Friday. And as I mentioned earlier, I'll try to grade your exams between today and tomorrow. Definitely you'll have them graded before the next class. So yeah, I'll see you on Friday if there are no other questions.
Thank you, Professor. Have a good one.
Okay, see you.
Thank you, Professor.
Bye. Bye.
Yeah.
Thank you, Professor.
Have a good day.
You too.